Yeah.
I just haven't felt really affluent enough here to do it. And of course I'll have to get 3 copies made.
You can.
I've got one of those cubes which is in the photograph.
How's it for you?
So you got it.
Yeah, we saw them.
They've been around, I think.
That's what it was. I'll give you this. I'll give you this. They already have it. Been having Billy's
Hey, Grandpa.
stuff in those sandwiches. I
I was sitting there on sleep.
Photos.
I got an idea.
And they're in the discs.
That's beautiful.
Sweet thing. However
That's
you want.
special.
Yeah, I hope to try it.
You have like a nameplate on
No, Tom told me.
Finally ready?
there? Are you ready, Tom?
Yeah.
Okay.
Up this is going.
I guess you want to leave the light on, don't you?
Yeah, this is bright enough that we can, I think everybody can see that thing. I get to talk tonight on water and steam. Probably because I'm always in hot water and full of steam or some such nonsense. But the steam is, as you probably know, is the key to the Stanley. Instead of the explosive push that an internal combustion engine gives to the whole drivetrain and eventually to the wheels, the Stanley with the expansion of steam gives a nice even push all the time to the motion of the car. And the power is applied through most of the engine stroke, especially when you're starting out. It's a real even application of the steam pressure. I did a calculation on the area of the piston on a 20 horsepower engine, which is 4 inches in diameter, and at 600 pound steam pressure, it's putting like 7 tons of push in the piston rods on the crank to get the thing going. Steam engine's the only engine that can develop maximum torque at standstill. So whatever the boiler pressure is how much torque you've got that you can apply to the rear wheel. The steam engine with the boiler and everything is a Rankine cycle type engine. Rankine cycle engines are ones where the fuel is consumed external to the engine, whereas an Otto cycle engine is the internal combustion engine. The fuel is consumed internally to it. Stanley's use a 2-cylinder engine, just like steam locomotives do, and it's 4 power pulses for a complete revolution of the crank. A 8-cylinder internal combustion engine is what's needed to duplicate that. Bill passed out this plumbing diagram that you saw last week for the fuel system. It's the same one. I didn't copy it over in the notes since you already have it, but I'll be concerned with basically the light blue and the dark blue of the Stanley. Starts out with water in the water tank. It's drawn up by the pumps, which are only operated when the car is in motion. From there, it's pumped to one of 2 places. If the boiler doesn't need water, it's pumped down through what's called the water automatic and then back to the tank. If the water level is low in the boiler, the water automatic blocks this path, and then the water coming off the pumps is forced up through the feed water heater and then through the boiler check valve and into filling the boiler. Obviously, with the fire and all underneath, it converts it to steam. It's drawn off the top center. For the non-condensing cars, out the back of the boiler. For the condensing car, which is shown here, this is for 735. The steam then comes out, goes through a coil above the burner for applying superheat. Then it goes on back to the engine. The exhaust off the engine is what's used in the feed water heater to heat the water going into the boiler. Comes off the feed water heater, goes front to the condenser, where most of it is condensed back to water, and that water is returned back to the tank. I'll be talking about all of the components in that water cycle, steam cycle, tonight. If at any time there's been any questions don't hesitate to ask them.
Bob.
Yes.
So then the condenser, that's something that I've been confused on. The older cars don't have condensers and the newer ones do?
Right, you'll hear me refer to non-condensing cars, which are the coffin-nosed cars, and condensing cars, which more look like the standard old-time internal combustion engine car with a radiator on the front, except it's not a radiator for us, it's a condenser.
So the condenser is just a radiator type fins?
It's a Mayo radiator.
What's a Mayo radiator?
What is that thing doing?
Screensaver.
Oh, okay. We're gonna go to SETI real fast, okay? It is a standard radiator as far as construction with tubes.
Okay.
And then the fins all on it. Bolted cans at the bottom and at the top onto those. So you can take them out and get them dipped and get all the steam oil and everything out of them, clean them out. Originally, when we talk about the condensers, they were V-shaped. A lot of problems with them. So they eventually went to the flat versions
Thank you.
of it. He gets the screensaver turned off. I'm going to have him move to a picture of one of the non-condensing water tanks. It's the condensing water tank. This one. This is one of the condensing water tanks. It happens to be the one that's in the back of the 76. As you see, it's copper. Typically, they were 15 to 45 gallons capacity for the non-condensing cars, except for the mountain wagons, which Tom told me was 50 gallons for some of the 1915, 1916 models of those. This is more just an access port to get in and clean it out and that sort of thing. If you look at the cars, out the back of the car is where the actual fill is. Unscrew the cap, put the hose in, fill them in the back. Standpipe inside overflows, and when the water runs out, the tank is full. They have a sight glass. It's not quite this short, typically a lot longer, mounted somewhere on the side of the car, driver's side of the car, that indicates how much water you've got in the main supply tank, to give you an indication of that. I'll flip to the non-condenser tank, which is that one. This is a picture of the non-condensing tank. This one happens to be under Tom's 735, which is also copper. I have a 735 and the thing was galvanized. So I believe, Tom, they came in both.
Yeah, Bob, I think you're backwards there. You called the 76 condensing and you meant non-condensing.
Non-condensing.
This is condensing.
Right.
Yeah. Yeah, they had both steel and copper, apparently.
Essentially a copper tank. In the center of the bottom here, you take the plug out and there was a strainer. The intake line actually comes in and drops down to the bottom. The tank comes in the side, drops down. There's a strainer up over that to collect crud and all. You can unscrew that thing and the whole strainer and all drops out for cleaning. This little rubber hose and all that you see up in the corner is actually the return line from the condenser coming back in to run the water back into the tank. These tanks, as you can see, are kind of a triangular trapezoidal shape, held on with a couple of straps and some bolts through the floorboards. 25-gallon capacity for them. Stanley advertised about 250 miles in some of their literatures, which you could get on a tank of water. It's been my experience that 75 to 90 is what I've been getting out of my car. I guess if you had a good flat area, cool day, and good condensing going on, you might get a little more than that, maybe up to 150 or something like that. You fill these through the condenser. So you take the radiator cap off, condenser cap off, stick the hose in there. There is a line that goes up into the tank, an overflow, that because of the oil that's in the water, once this starts to overflow, you start letting the oil run out off the top of the surface of the water, and all. We'll talk about that. But these are set up with a standpipe essentially in the tank that when you get them almost full, the surface oil and all will run down the standpipe that indicates the tank is full. Plus it's a way to float off the oil that comes through for the engine. The gauge to indicate water level in that tank is usually was in the top of these tanks. It's right on the floorboards, right underneath, right in front of the front seat, where the driver was. A little gauge to indicate the water level in these tanks. These cars also had, and there's another pipe, you can barely see it right in there. Both the non-condensing cars and the condensing cars had steam siphons on them. You could run a hose out to a water source, the non-condensing cars, a horse trough or something like that, turn on the steam siphon, or steam ejector sometimes as they're called, and suck up a load of water. I was surprised about how powerful the thing was. I was at a hose filling a 5-gallon bucket with mine, cracked the steam valve to get it going, and gurgled a little bit and started, and I said, we'll see what the thing can do, and I opened up full turn on the valve, and the water like went woof down in the bucket, so it'll move some water pretty quickly. Any questions on the water tanks? Tom, if there's one in the pumps. Pumps are what pump the water from the tanks. This one. Around, this is a picture of the pump box of a non-condensing car. These two pumps right there are the water pumps. They are 1.25 inch stroke pumps, at least for this 20 horsepower car. The pin diameter is 5/16 diameter there. Piston until 1908, and when they went to 5/8 until 1914. There are check valves here and here. There's an inlet check into the pump as well as a discharge check. Both of those checks are using 7/16 inch balls in them. These pumps are driven from the engine. This is the crank with the drive rod going back to the side of the engine. Herb will talk in 2 weeks about how this is all driven and this sort of thing. But essentially the pumps are running directly from the engine at a quarter of the speed of the engine. The non-condensing cars, the condensing cars, I'm going to go to a different picture, which, right there. This is the pump box, a condensing car down along the side of the frame rail, really underneath the passenger seat. The pumps are sitting here. This was kind of hidden. It's a long stroke pump. Some literature I have has it at 4 inches of stroke. I'm not quite sure if that is 4 inches. I need to spin the tire over on one and actually see what that stroke is. I have it 4 inches in the notes because I had it out of some other notes that it was 4 inches. So we may need to question that. Still uses the same 5/8 inch diameter pistons. They did change to 1/2 inch diameter check valves, or check balls in the check valves. You can see the caps of here, the inlet and the exhaust, the discharge check valves. Condensing cars also had a little triangular rod on top of the check valves, probably as like a shock dampener, so you don't get as much clanking and all going on. So they were a little bit different than the non-condensing pumps. The drive for these is through, again, that rod. They're driven off the back axle through a gear and a crank arm. Again, Herb will talk about how the pumps are driven, how they're set up and that sort of thing. They also provided a hand pump up in the center of the car. It's connected with the fuel pump that Bill talked about last week. There's a valve on them that you can shut them down so they're not working. They're about useless. There's about a shot glass of water each time you stroke it. And when you've got a boiler with about 8 or 10 gallons of water to get into it, you'd be there a fair amount of time pumping water with that little thing. So they are almost useless. They are plumbed in between, basically on the back end of one of the pumps, and they actually use the check valves of the forward pump. So there's no check valve in the hand pump casting body itself. It actually uses the checks of the main power pump for the water flow. I'll discuss, a little more of the operation of this in a little bit when we start talking about how the water and all flows through. The whole system, you've seen the various Stanley valves, two styles of them here. This is probably the more classic. It's basically a bronze or brass casting. It's got a nut on it. The packing is actually put in the top nut, and it's screwed down on, and then there's a lock nut to hold it in place. The other style is the more conventional with the nut and a follower gland. It's got a stuffing box that you can put the packing in, bring it down, pull it up tight. The handles, you'll notice, are aluminum cast. On some of the real early cars, they were wire formed handles. There were also a different type of handle that was used on some of the later condensing cars. Basically a single stem, weird pitch thread, and I don't remember what it is offhand. Two different tapers, 15 and 30 degrees on the ends of these. They basically just sit down into a V that's in the bottom of the brass casting seat.
Are they difficult to rebuild, as if you have a leak on
On packing?
No, either under shaft or the body inside the
I've had some of these where they're pitted here, and just had a machinist make new ones, no problem. You'll get these, especially on some of the blowdowns for the boiler, get a little bit of grit in the base of them. They grind in there a little bit, and then they will weep, and it's real easy to put these in a lathe and just touch up the point on the ends of them, match it. Just
You have to take the handles off?
the handles are basically, it's a square fit put on, and then the top is peened over. So I've only ever taken handles off of one when I've had to change it. Put a new stem on it. Yes.
You ever have to remachine the seat and the valve body?
We have on, Herb has on a couple of them. He had to make a cutting tool for the fit that. The other thing you've got to watch is to get, you take one out that's got a certain size taper on it, to make sure that's the stem you put back in it. The other type of valve that Stanley has in some applications, they don't have the taper, they actually have a ball, steel ball on the end of it. And it's a ball that sits in the seat. I had trouble with one of those. There's a bypass valve in the water automatic, and the way it was plumbed up, the water was on the back side of that ball, if you will. And I shut the valve off so I could fill the boiler up before I shut the car down. And then when it was time to leave, I screwed the valve back up. Well, the steel ball isn't press fit on the end of the shaft, so it stayed seated. So I kept flooding the boiler. I couldn't figure out for the longest amount of time what the problem was. Took it apart, started working fine, put it all back together. Next thing I know, it was fouling up again. So that was that had been plumbed up wrong, and then when I replumbed the car, I plumbed it up wrong again. So learning experience. How those were. Yes, Steve.
I think that there's no stop on that valve. If you unscrew it too much, it's going to end up in.
You're going to blow it out, yeah.
That's it. Okay.
These valves, if you look at the porting and everything in here, one turn is basically all you need to be full open. So they're real sensitive to throttling and some things like this. You can crank them down and just crack them off a little bit, and they throttle pretty good. The other thing is, especially on the ones that are for the boiler blowdowns, they may weep a little bit because now the seat's been cut, so you crank it down a little bit. The valve is all nice and hot and expanded. Then when the boiler's cold, you can't get the bloody things loose. And I've kind of got a reputation around for cranking them down too tight. And I've tried not to, but to get them tight enough that they're not dripping. And going back myself, and couldn't get them open. I mean, you really got to get both hands, and a lot of them are in places that you can't get decent leverage on. You wonder, how did I ever get this thing that tight? Because now trying to get it loose won't go that easy. Once you're pumping the water into the boiler, you need to have an idea of where the water level is. And the first generation Stanleys, the real early hot years, O years Stanleys, had a bucket type arrangement that I don't even want to try to go into explaining how they work. Little bucket that floated on the water level, a cable that came out that indicated what was going on. They soon went to what they call an expansion type or a brass type, where it was a casting and with some tubes in it, and it dealt with the expansion of the water in a secondary tube that wasn't under pressure to indicate where the water level was in the boiler. That thing, when you look at the patent for it, had to be a nightmare to put together and get it balanced and working and everything like that. And they greatly simplified it into something we affectionately call the Ouija tube, which is that. It's essentially properly called a 3-tube indicator. And the way this is set up is the middle tube is connected to the top and the bottom of the boiler. So it is actually the water column. It's indicating water level, seeking in here equal to where the boiler water level is. Then you have a secondary tube that's welded along the side that comes out and goes through a tube and goes to your actual water indicator on the firewall. And a little screw in the top of this thing, take that out, run water into here till you're getting water coming out. They're probably sitting in the car something like in that height arrangement. So once you get the water out of here, you'll be at this place. While you run the water, you plug it. So you've got that whole line solid full of water. Well, once the boiler is fired up, the water level seeks position in the center tube equal to what's in the boiler. And it causes, by how much water is in here, the water being cooler than the steam, how much heating is done to this tube. And the more that this tube is heated, the higher the water level rises in the indicator. So just backwards from what we call a dead side indicator or model type indicator like you'd see on a steam locomotive, these work just backwards. When it's low, the boiler has got plenty of water in it. When it's high, you better find out why you're not putting water in the boiler. Now the problem with this is this gets hot when the car is not standing or just in operation. So the third tube over here is water that the pumps are pumping. And remember, the pumps are driven off of the engine, so the pumps are always pumping. It's either going back to the tank or it's going to the boiler. So that water is always circulating through here. And that's actually what's keeping this cool and allows it to work. If you let the car, you come up to a stop and let the car sit for about 15 minutes, you'll see the water level come up in here and they'll sit there and bubble a little bit. And that's because there's no cooling going on this, and the heat from the center section is heating this, causing bubbles of steam to form, and then they cool off, and it's causing the water to dance up and down in this. The valve that's here on the bottom of this is the blowdown, just to make sure that this thing is clean. You can be driving along and you normally see, especially when the water is about ready to make a level change in here, you'll see it start to bounce a little bit. And it'll start bouncing pretty good and then it'll drop. Or if it's low, it'll start to bounce and then it'll jump up. So you kind of get used to the car after a while and how this thing works to watch that bounce. Well, if it starts to get a little sluggish, it's an indication that perhaps the center tube is getting a little plugged up, something between the circulation for it, and you need to blow the 3 tube down. And usually you can just blow it down. When you do it, you get a lot of steam in here. Usually the water will jump up in the indicator. Then as soon as you start driving again, it'll come right back down. Yes, Joe?
Does that tell you just whether you're high or low, when you need water or you're okay? Or does it actually give you an indication of roughly how much water's in there?
The original brass ones were real short and basically told you, yeah, you got enough water, no you don't. These do give you a pretty good idea, but you remember we're going to be talking about boiler heights that are
Bigger than that.
12, 14, 16, 18 inches high, which is, so this has got to be positioned, first of all, about where you want the water level to be in the boiler. And it gives you some indication for what's going on. One of the things also that you get used to is, like the 76 has this belly tank underneath that you can siphon water up into the main tank that the car runs on. Well, from going through the siphon, it heats the water. Well, now the water that's circulating through here is hotter water. So this thing isn't cooled quite as well. So it affects the reading that you see on this, because it's going to read higher. So you'll have the tendency to say, oh, I still need to put water in, when it's really not getting the cooling that it once had. So how hot the recirculation water is also affects what this thing reads and everything. And most of the guys that have had these things on cars have replaced them with the glass tube indicators, the standard dead side indicators. The problem with those are we're running 600 pounds pressure. The glass tubes are essentially, their safety factors around 600, and they will occasionally crack and blow out. Once you learn how to run these, I rather like the darn things. They're neat. As far as the toms that we had in New Hampshire last year, we were the only ones running the whole week on these things. Never scorched a boiler, never did it. You know, the guys had gotten rid of these things. Couldn't tell what. They just don't like them. The other, I've got a picture of one of the kidneys. The other indicator is this one. That one. This is what they've referred to as the kidney. It sits, this side's on the end, the boiler side of the firewall. Just the gauge side is sticking through the firewall so that you can see it. It's right down by your feet. And essentially, there's an arm in here with a float that goes. There's a shaft up through here, and on the back side of this, there's a magnet. And the magnet is through this cap to the, and this one's missing its needle, but it just magnetically couples to the needle that's on this side. And that's how these operate. So the float that's moving in here just causes this, you hear it banging. Causes the float goes up and down, rotates the magnet. The magnet moving here tells you whether you've got high or low water on the indicator that's here. These are, again, through the bottom, through the top pipe, to the top and bottom of the boiler. And then there's usually a valve in the side here for blowing this thing down. It'll get oil in here and get the bucket full, give a false reading, so you need to blow this thing down as well.
Which one of Tom's cars has one?
740 has one, 735 has one. Even though it's a condensing car, the 725 still has the conventional Ouija tube on it. Those were invented, 1917's on the patent. They were invented by someone else, and they gave all the rights to the Stanley motor car company. Feed water heater, which is right there. Up along the right side of the car, in the frame is a feed water heater. It's a pipe about that big in diameter. What you're looking at is the back end. Here's the steam engine. The exhaust steam coming off the engine is fed in to the back end of it. The steam works all the way up towards the front of the car, and then it's ported off the front of this thing and goes off to the condenser. Inside of here, pipe comes in the side, goes the length of it. I guess it stands about this high, goes all length. Goes down the bottom, there's a block. It's actually mounted in the back end here, makes a U, and goes back up to the front and comes out the side. So it's basically heavy wall, real heavy wall, because it's 600 pounds of water pressure inside that, because it's boiler pressure when it's pumping. So it's a heavy walled copper pipe.
Copper?
Copper on some of the ones. Mine came out as copper, went back as stainless. Tom bought some replacement ones that are copper. Real heavy wall stuff. And copper's got the good heat transfer and all, which is what you're really trying to do, get the heat out of the exhaust steam into the water going into the boiler. So that's essentially all this thing is this is the back end of it. Usually the front end of it has a screw cap in it. You take the whole assembly apart for cleaning it and that sort of thing. That's I call it the feed water heater. Sometimes it's the heat exchanger. But it's basically to heat the water going to the boiler. There are check valves throughout the car, and we didn't bring a sample of one of those down. But essentially they're little ball check valves that are used throughout the whole system. Pumps have check valves in them, but they're part of the castings. There's a single little check valve. It's maybe the diameter of your thumb. It's a little steel ball and an inlet in the bottom of it, outlet along the sides, a casting screw nut in the top of it. You'll find those in various locations in the fuel system and in the water side, part of the Stanley water system. The boiler stuff is next thing. Let me see these pictures again if you will, Tom. Here, we'll look at, let's do that water glass one. We were talking about the water fill. Here's the water glass. Bring up some more. You'll see that the water level is up an inch, inch and a half in the bottom of the glass. Car sitting cold. Generally, when it's running, tend to run at about the middle of the gauges. Once it starts to come up, it's a signal to put on a second pump or start pumping more water because you're using steam and water faster than you're replenishing it. When it starts dropping down in this area is when I turn a pump off, something like that. So I kind of use, these are all typically mounted between the two gauges on the car. This is the main fuel pressure gauge. That is the steam pressure. So they're mounted between those, and I just kind of use the diameter of the gauge as an indication of where things are bouncing. Just watching. You'll see it sit here nice and solid, and then it'll start bouncing, and it'll either drop down or it'll go up. But they tend to have pretty set locations where the water levels want to sit. Okay. The non-condensing car boilers. This is the one off the 78 flues. Here's the throttle line going off the back. The burner is obviously underneath this. It is a fire tube boiler. And then the smoke bonnet on top, smoke box on top, and then it's ducted off the back, drops down alongside, goes out and duct all the way to the back of the car to get rid of the combustion products. Flip to the, where's that one? This is a picture of a boiler in a non-condensing car, or excuse me, a condensing car. Again, you see all the tubes. It's got the top off the throttle for the condensing cars, goes off the side. The water is coming up. I mentioned check valves. Here is the boiler feed check. So the water is coming in through here, going through the check and going in. This pipe is actually extended down into the boiler, and it's below the water level. So you're not running water in through the steam, you're actually putting the water in a few inches off the bottom of the boiler. So the water is actually going in and mixing with the hot water that's already in the boiler. These have a habit of corroding up on the inside. That's why it's extended, and you can pull the plug off the top and run a wire down through it and clear it out. Make sure it's clean. Okay. Let's see, I think we've... Yeah, let's do this. This is the 3-tube. This one I did, 3-tube indicator. This is the 3-tube indicator. Here it's installed. Here's the line that comes off and goes up through this copper tube to the firewall to the indicator. Here you can see the center tube goes down here and actually goes to a boiler blowdown and underneath the car. Comes on, up, and goes into the top of the boiler for the steam side. And then this side of it over here, and the check valve and everything is part of the water circulation loop for it. Okay. And we've covered all of those. Leave the one for the boiler. The Stanley boiler is the key to the car. It's really a can of energy. This is one of the construction of one. This one is a non-condensing car boiler, relatively small one. We'll talk about the setup of it. Storage battery in your car stores a lot of energy for when you need it. 300-400 amps when you're cranking it over, and then you put it back. The boiler's doing the same thing. You've got a lot of water in there. You're storing a lot of energy in the water. So while the car and the boiler may be rated at, let's say, 20 horsepower, that's its average horsepower rate. You can actually get a lot higher horsepower rates out of the boiler for a small period of time. So for example, when going up the hill, the boiler can actually deliver more horsepower than its average rating, so that when you're going back down the other side, it's replenishing itself. You're adding water to make up for a lot of the steam you're using. You've got the fire going down the hill to bring that water back up to the temperature it needs to be for 600 pound steam. There are fire tube design, which means the exhaust gases are coming up through the tubes versus a water tube type design. That also is what gives them a lot of their storage capability. You've got water inside that around all those tubes. Early boilers were set up to run at 400 psi. They moved up to 600 psi for the later cars, the condensing cars, and this sort of thing. And typically, the hydrostatic test where you fill these up and check them for leaks is done at 1,000, 1,200 pounds of pure water pressure. They came in 14 and 16-inch diameters by 13 inches high. These were the very early generation cars. They then moved to an 18 and 20-inch diameter, 14-inch high when they kind of standardized on the 10 horsepower engine size. Moved up to a 23-inch diameter by 14 for the non-condensing cars at 20 horse, and the condensers through 1917. Starting in 1918, they moved up to an 18-inch high, 23-inch diameter boiler for those condensing cars. And then the big 30 horse cars all had 26-inch diameter boilers on them. Typically have 700 tubes inside a 23-inch diameter boiler. The 26-inch ones for 30 horsepower had, I think one of Tom's had 999 tubes in it. So there's a fair amount. The walls are 3/16 thick steel. 1/4 inch for the smoke box, what I call the top flue sheet. A little bit thicker for the bottom flue sheet, 5/16. I built a condenser boiler for my car. Construction is essentially that, where this plate represents the bottom flue sheet. Under the fire would be where my hand is. This is the top one where the smoke box is and all the gases are going. Of course, you'd have the round can, so your water's around all the tubes. Had this one drilled so I could work with putting the tubes in and some things like that. We'll talk about how this thing is constructed here in a minute. Give me this one. This is a bunch of pictures of the one that I built for my car. Essentially got the round shell that was rolled all out of boiler steel, and this one has the bottom flue sheet drilled. For all, as you can see, there's 636 tubes in this one. Put the two plates together, put them on a mill. These are half-inch diameter tubes, and let the CNC mill just go and drill. It took about 10 hours just to drill it. Then it had to be cut round, and then it had to have a taper put on it so that it could be welded. Flip it on to this one. Bottom's been in, we put rods in. Here's the top flue sheet sitting on it, and it's just been tacked a little bit around the edges, keeping all the tubes obviously in line for the welding process. That little piece right there is the one you're seeing here. There's also a set, once it's all welded, there's a set of 1.25 inch wide bands, as you can see on this, a little smaller on this board, that go around the top and bottom. That's them laying here in the background. Some added strength, plus it's where some of the clips and all go to hold this in the car. The picture here is of about 300 of the tubes installed. They're pushed through. Once they're all through, two things you can use. One is just a standard punch like that to spread these tubes, or you can roll them with a roller that's made for it. A little device like that. There's 3 little rolls here on the end, and one of the tubes, just like that, this goes in. Take a power drill and run on the end of it, and it actually flares this out against the side walls of the flue sheets. You can see this one got a little bit of a ridge in it from being rolled. These, for this application, were good enough that to set how, this is a tapered pin here that moves, that drives these rolls out here on the end apart. And all that, there's a couple ways you can do it. One, the real technical way to do it is to put a pneumatic torque wrench on here and let it run down for a certain torque. It gives you uniform spreading on all of them. The second way to do it's the way I did it, and you just stack a number of washers and you just run this thing down till it stops, and that's it. The olden days, they were just spread with something like that. The non-condensing cars all had copper tubes in them, and if you look closely at the thing here, it looks like they're steel, but they had a little steel ferrule that they put in to help hold the copper and keep the seat. So they put the copper tube in, put the little steel ferrule in, and then use just a punch down the hole, hit it a few times to spread it. Problem they had, and Herb will talk about lubricating the engine, is you have to put oil in with the steam to lubricate the engine, which means that's coming out the exhaust, going through the heat exchanger, coming through the condenser, going back in the water tank. It's getting slightly in solution with the water, pumped by the water pumps into the boiler. And it was laying on the bottoms of the boiler and causing the bottom sheets to get hot enough that the copper tubes would start to leak. So they went to all steel tubes. And there is that one, change that they made to the boilers for condensing cars. You weld all the tubes on the bottom. In fact, that's what part of this was for, was we were setting how far the tube had to be extended past the flue sheet, because actually in TIG welding it, we were melting the end of the tube down to be the steel for the welding. So it was done, this was the practice sheet for not only me rolling, but also for some of the welding and things like that that we were doing. So condensing boilers all have the tubes welded. Non-condensers had copper tubes, not welded. You also see now the 2 rings that we put on the top and bottom of it. Okay. Go to that one. Once all the, you enlarge this one just a little bit. Okay. You can see this kind of a line break down through here. When the tubes get in, they're kind of like the tubes on here, they're different lengths. So you need, if you want it to look nice, you need to yeah, that's the row. These have been trimmed, these have not been trimmed. And basically you have a end mill that you put a guide over, and it has a axle shaft. This is kind of something I put together that you stick down in each tube, and it essentially just knocks each tube down. This sets the height. So you go through each tube and basically machine the end off a little bit just to get them all equal. Once you've got them all set equal, and part of the problem I had with the one that I built is when the 2 flue sheets got welded, it took a slight curve in. So the boiler was actually a 1/4 of an inch less in height in the center than it was out around the edge because of this little dish that both of the flue sheets took. And to be able to put the little flare and all on them, I wanted them all equal. So I put together the little trimmer, and that's why you see the line here. These have obviously been trimmed all at even height. Those haven't been. Once you trim them, a standard counterpunch down the inside of the tube to deburr the inside, and a plug cutter on the outside to deburr the outside of the tube, and then they're ready for rolling and expanding into the flue sheet. And when I rolled them the first time, the standard calculations that they give you for boilers, and I said okay, and there was a range calculations. It was like 5/1000ths of inside diameter difference, and I said, well, I'll stay on the small side of that. Well, it turned out when I tried to hydrostat the boiler, I couldn't get up over about 300 pounds pressure to it. So then I said okay, and it turned out I took 2 washers out of the roller and rolled them all again, and put it on the high side of the number, and then I passed the hydrostat. So it's that much. The problem you've got is if you over roll one, you can end up starting to flatten the holes of the ones around it, and they won't seal. So it's a trick of getting the rolling just right when you're doing those. Tom bought a boiler that was done with one of these, could get it to pass hydrostat. We spent 3 or 4 nights deep on that thing just to do this. Having done the rolling, done the pin, I'll do the rolling anytime. I ended up, when I rolled that the second time, I rolled that whole thing in 2 hours. Because you basically put it in, roll it until it's stuck. Cut the air pressure down on the drill a little bit so it just, as soon as the washers come up tight, it stops, and just stick it in. Had the reverse lever on it back because you have to reverse it to back it off, and just right on down through there. So 636 tubes in 2.5 hours just to roll it. The tubes that we're using are typically 18 gauge wall thickness, good to 1,000 pounds. It's hydraulic tubing. Boiler steel and all for the tops and the bottoms. If you take all the area around all the tube and add it all up, and have this thing sitting at 600 pounds of pressure, there's 80 tons of force trying to push it, blow it off of there. There's a fair amount of pressure packed up behind it. There's also that amount of pressure on the sides, and the walls aren't that thick. So there are, as you see on this, 3 layers of piano wire that are wrapped in the boiler. There's about 25 pounds of tension put in the wire. And it's, Stanley was 048 wire. When I rebuilt one 054 diameter wire, it's 300,000 pound tensile strength wire. You can't bend it to terminate it off. You've got to heat it and get it so you can even bend it and work with it. Another purpose of these rings is there are drift pins put in there, and that's actually what you loop the wire on. The setup that I had done here is, this is just a little DC drive motor that I run off of AC variac and a couple pillow blocks, and I made the plates up with bolts that go through the flues, and just basically turn up the variac and the drum spins. The wire came back to a spool, 2 pieces of metal with a groove in it that I just clamped down to get the tension that I needed, and just turned up the variac, spin, and just spun it on there. And put 3 layers to it, yes.
So where can you buy that wire?
I got it through M&P Custom Design in Kennett Square. They ordered it from a wire company up in Connecticut. The thing that there's close to a mile of wire on a 23-inch diameter boiler, and they sent it as 1 spool, and it came as a donut, no core or anything else. No problem. I made a wooden core, put an axle through it. Opposite to this was another fork truck that had that on it, and I figured just spool it off and wrap it on here. Well, the first layer went fine. The second layer went fine, but partway through the second layer, it started to get snagged. And by the end of the second layer, I had a mess on the spool that I had. And I ended up throwing away the 3rd layer of wire because it got so knotted. Because it's all got to be one continuous strand on the boiler, or it should be. So I had to order another roll of it. And they won't spool it. They won't put it on spool like you buy electric wire. So I got another donut of it. And I ended up getting one of these LP gas bottles. It's about this high. Throwing the wire down over it, putting the spool, welding wire spool, on top of it, and spinning it off. And it turns out that once I saw how it was done, they actually rotate the whole thing. It's for like these automatic wire wrappers and things where as they spool it out, they turn the whole thing, and it's got a hub and all. And the way I was trying to spool it off ain't the way you get it off. And hence I got the knot. So I've now, if I ever do another one, I've got to get them to cut it in 3 individual pieces, and I've got to take 45 minutes or so and spool it so that I can wrap it this way, because this, once you get it gone, it wants to go pretty good. But you've got to be able to feed it. In fact, the second layer that's on here actually got put on twice because it was knotting up enough that this got loose. And if the layer gets loose, when you put the 3rd layer on it, you've got wires that aren't quite tight, and the 3rd layer pulls down in between it. And now you've got an uneven wrap. So I actually put the 2nd layer on twice. So the second time I can get it tight. You learn all this stuff the first time you build one of these things. Most guys that have...
Work at a special rack for that, an open spool of wire.
But it spins and everything, as it's discharged typically, the ones I've seen.
It just rotates like a wheel on wire.
Yeah. But you can't take it and put a spool inside it.
End, no. You've got to...
Well, I didn't realize that the way they had wrapped it. As soon as I saw it, when I got the second one, how it was coming off, it was fine. A lot of guys have condensing cars, and you can't get a condensing boiler. The guys that are making boilers only want to make the copper tube ones. For one thing, they're a lot easier. So they're running copper tube boilers in condensing cars and putting some sort of steam oil separators, something like that, doing a lot of extra flushing, those types of things. Now, I do have a steam oil separator that I added to it anyway. But I wanted to make it back the way it was originally, steel tube, boiler, welded, that sort of thing. That's the way I built it. Show that. Oh, I should do this one. This is just the plate boilerplate sitting on a CNC mill, was drawing the rows, measured a couple of Tom's boilers, did a computer drawing, sent the computer drawing down to the guy that has this mill. He fed what's called the DXF file right into the mill. I only did half the boiler. This table didn't have enough run to go the full 23 inches, so we could do half of it. And so he drilled half of it, put 2 pins in the table, flipped it over, and drilled the other half. And then same computer program gave it the 21 inch or so radius or diameter that it had to be cut into for the plates and put the bezels on it and that sort of thing. So that's the CNC drilling it. That same machine right now is drilling the grate for the 607 that took off, I guess it was 2 weeks ago. That's got 4,472 number 54 size drill holes in that thing. And it took about 20 minutes, did the computer program, downloaded it to Tony down in Middletown, and he's going to rack it up and just let this thing sit and drill.
And that's only a 10 horsepower.
And that's a 10 horse, yeah. This is just the flues all being cut on a bandsaw for it. And then there was one more. It's this one. Before you can all put the flues and all in, you've actually got to drill the top and the bottom for the steam discharge line in the top 3/8 inch for that. You've got all the boiler blowdowns around the edges of it. You've got to drill all those. All the water fill into it, the steam lines that come off the water automatic and the water level indicator. So you've got a number of holes to drill in both ends and tap out for 1/8 inch, 1/4 inch pipe. One or two pieces of 3/8. So all that has to be done. That's all that setup is. Third layer of wire. Okay. Show that for a minute. Once the whole thing was done, put together, Tom has a hand pump. He had an old pump off of something that I had made a little base for. Hook a garden hose up to it, fills up the boiler so she's absolutely 100% full. Go to the other picture now. And basically with the handle and all, you pump up hydrostatic pressure. It bleeds off a little bit, but there it's sitting at 500 pounds. The boiler itself sitting solo with just plugs in it and everything. The one I built was tested at 1,200 pounds. You can't go that high in the car because you've got the steam gauge now hooked up, so you're basically looking for water leaks and things like that. The car should, if you get up to 1,200 pounds, you've got to get out and get going. So this is basically a 600 pound test, making sure that the throttle holds, all that sort of stuff, so that you have the hydrostat in the car. Around the bottom of the car or bottom of the boiler are blow-offs, depending on the boiler. When it was made, you can have anywhere from 1 to typically 4. Typically they're in the corners. Some of the cars only have 1 blowdown, some just have 2. I actually put 4 on this one for blowing down. In fact, that's one of the blowdown handles. They're the standard valves, typically like that, around the car. You'll see them in the rear wheel wells, places like that, for blowing down. The condensing cars, maybe not quite as bad because of the recirculation of the water, but the non-condensers definitely, as you go through a day, you fill it 4 or 5 times, all the impurities are staying behind or staying in the boiler. So blowing it down at the end of the day is getting all those impurities out of the water, that sort of thing. The non-condensers, as I said, recirculate a lot of the water, but they will also thicken up with crud. Also, oil that's going in the steam is coming back in those. So typically when you blow those down, as you get down towards the bottom, most of the water out of the boiler, you'll get a load of oil blowing out of those. The parking lots where we go for steam tours get a nice sheen to them by the end of the week from the various condensing cars and all blowing down. So on and so forth for all of that. there are several types of safety devices. You can see one of them here is standard pop valve. That's not a Stanley type pop valve. They're a little smaller. See the springs and all in it. But the cars have pressure relief valves on them. Releasing steam somewhere around 700 pounds or so. Gets too high. The other problem is if you run too low of water, and the initial boilers, Stanley built the ones like this, they put, look, if you think of an F laying that way, the top leg went in the center of the boiler and went up a little ways. The other leg went in and didn't go in quite as high. And if you had enough water, this whole thing was full of water. And so it was all, the horizontal leg was down in the fire. So it was staying full of water, and as the water would flash to steam, new water would come in to replace it. Well, at the end of the F leg was basically a piece of pipe with lead in it. So that the water level got down low enough that both of the legs of the F inside the boiler became exposed. Didn't take long for the fire to make steam out of all that. Then this could get hot enough that the lead would melt. You had 600 pounds of pressure behind it. This would blow out, and now you knew you had low water problem. Once it's all cooled, you had to wait until everything cooled off, and hopefully you had one of these in the toolbox, take the old one out, put the replacement in, and then use the little hand pump to fill this stupid thing back up. Yes, Joe.
I have the piping for that in my car. I'll bring it down later.
Oh, okay. So that would be about the only time that you could use that stupid little hand pump. Of course, if you didn't have boiler pressure, you might be able to find somebody with a hose and had the hose fitting and fill the boiler up, open up the throttle and just let the air out the engine or something like that and fill it a little faster if you were lucky enough to blow it out somewhere where you could do such a operation. The low water shutoff, photo of the 3 tube. That's probably not in this set. Probably the first thing I'll worry about. There is this device, which is the low water shutoff. And in the one picture that you saw in the car of the Ouija tube indicator, you saw something else kind of off at an angle. It was low water shutoff. And boiler water is in the center tube. And as long as it's got sufficient water in it, this thing's fairly well contracted. But once the water level gets low enough, this gets a lot of steam in it, it expands, pushes up on this pin, which is a needle valve type pin like inside the valves, and fuel for the main burner is running through this end of it. So it shuts the fuel off. So it's the low water shutoff. Now, if everything is working right, you're not going to get to that level because one of two things is going on. In the non-condensing cars, you've got control over the water from the pumps. 2 pumps or 2 valves, one right up underneath the steering column that basically sends water to the boiler or not to the boiler. There is a second valve, usually down between your feet, that turns on and off the second pump. So if you've got the valve at your feet open, it means the second pump is not pumping water. It's recirculating water back to the tank. And if you close the valve on the steering column, you're putting water from the one pump into the boiler. If you open that up, then you're recirculating water back to the tank. If you shut the one at your feet, but you still have the one open on the steering column, you're still recirculating water. It's going back to the tank. It's not until you close the one on the steering column that both pumps actually start to pump water to the boiler. So non-condensing cars all had manual water controls. You had to watch what it was doing. When they got into the condensing cars, they got the water automatics, which is this device. And this end piped to the bottom of the boiler, this end to the top. And it sat at a slight angle to the side of the boiler. And depending on where the water level was, this center tube would either have water in it or steam in it. And as long as it had water in it, it was relatively cool and contracted. And it kept this valve stem pulled open. And this is the water coming in from the pump. This is the water going out to the tank. If you look at the diagram that you got with Bill, so you've got water flow from the pumps going through here because this is full of water. But when the water level in the boiler gets down, this fills with steam, it expands, it pushes the stem, the valve shuts off here, so now the water coming from the pump is stopped from going back to the tank, and with the natural pumping effect, it builds pressure. And as soon as it builds 600 pounds pressure, it lifts the boiler check and squirts into the boiler. So this is the water automatic. I mentioned that some of the Stanley valves had ball type, had steel balls on the end of this valve. This is one of those steel ball type valves. This is not one of the V cone type valves. It's actually the end of the stem is a ball bearing that's set on the end of it. But full of steam, the pathway to the tank is shut down. The pumps build pressure. Water from the pumps is circulated through the heat exchanger up through the boiler check and in. With this thing full of water, valve is open. This is flowing right back to the water tank. Don't have any samples of it here. You've seen the dashes, you've seen the gauges. Another part of the water system, steam system, is the 0 to 600 pound steam gauge. Some of those, fair amount of the dial to indicate steam. So you get to the condensing car, the condensing cars, very small, little bit of motion. The 0 to 600 pound steam pressure. So you have steam indication on the dash. Controlling the steam that the boiler produces was the throttle. This is a throttle assembly for a non-condensing car. It has a shaft, it moves up and down. This one's got enough packing in it that I'm not going to be able to slide it. But essentially, comes steam from the boiler here. This line goes off, heads out to the superheater, back to the engine. It's called a balanced throttle because that's actually what the valve stem is. This is the one that came out of my car being replaced. And when the throttle is all the way off, this cone is plugging up on the seat in the back end of this. So it's sitting in like that. So there's steam pressure holding it shut. Once you crack it loose, steam pressure comes around it, but this little hole that's in the side hasn't started to line up with the port on the side. So now all you've done is push this off with very little pressure. You've got equal pressure on either side, and then when you slowly start pushing it down, you get steam coming down through the center of this core and coming out through the hole and out through the side of the throttle. So you're not pushing against steam, 600 pound steam pressure to move this thing. And that's where they come up with the balanced throttle, because the steam pressure on both sides of it is always balanced once you crack it loose. We need to go to the other disc, the last disc. The throttles on the non-condensing cars, pipe came up off the center of the boiler, came right back to the dash, and those throttles were at the top back of the boiler. On the condensing cars, they came out to the left, they were set at an angle, and the line came out and went down to the superheater. Take the throttle out, comes out. is the picture of a condensing cart. Here's the throttle sitting in on the side of the cart. Steam coming off the top. There's the throttle mechanism, the throttle handle going up on the steering column. And the line comes on down, goes to the superheater. So here's its position on a condensing cart. Non-condensing cart sits off towards the back. Okay, flip out of that one. This line goes down to the superheater. This is looking up underside. Obviously, you recognize the boiler. Here is the superheater coil. Now, what's not on here yet that makes up to this ring is the burner. So sitting in the top ring that's on the bottom of right under the burner is the superheater, and the steam is coming from that pipe, which is part of the throttle and all, comes down around the front of the car, in the front to the superheater, and from the superheater comes out, and there's a U-shaped expansion loop, and it goes back underneath the car, goes through a swivel joint and into the engine. So the superheater's purpose is to raise the temperature of the saturated steam, add energy to it. Saturated steam, saturated in water, 212 degrees room pressure, room temperature. The water at 600 degrees is 486 degrees Fahrenheit. So the steam and the water are essentially sitting at that temperature, superheat. The problem that you've got is as it leaves the throttle, pipes can be cool, air currents coming across it. Doesn't take much cooling to condense it back to water. The higher you can heat up steam, the more it gets to be acting like an ideal gas. And I put some technical numbers in the notes to give you an idea of what the superheating can do. If you can raise the saturated vapor at 600 pounds steam pressure to 1,000 degrees Fahrenheit, okay, you're changing the volume from 0.7 cubic feet per pound to 1.4 cubic feet per pound. You're almost doubling the volume, so you're getting a lot more energy out of the steam. So what it means is you actually use less steam. The more superheat that you can put in the steam, the less steam you're actually going to use. Now the downside of that is that exhaust steam is hot, and it's got to go through that condenser and get condensed back into water again. Those condensers aren't all that efficient. So you end up with the overflow pipe or the condenser tanks, water supply tank blowing steam out and cut your water mileage down. So you can make the engine real efficient, but unless you have a radiator that's something out of a big truck, you're not going to do too good with it. The condensers on the front of the car started in 1915 model year. Obviously just there to change the steam back to water. Let me just picture one of those. It's this one. Here is the water level automatic. This is the boiler check coming in. From the frame, the line coming up here is coming off the heat exchanger. This is a steam oil separator that I put on this car that was not original. Comes up and goes into the top of the condenser. The water then, steam as it condenses, comes off the bottom and then runs back around the back of the tank. Also, sitting on top of the boiler is the smoke box. It's basically a hood to collect up all the gases coming up through all the flues, directs it over the back, and goes on down the back of the car. Underneath, actually the condensers, it just dumps it out in the middle underneath the car in front of the water tanks. But essentially, these things, that one's a Mayo radiator. It's used as a condenser. Some of the cars you'll see will have a pressure relief valve on it. The oil circulating all the time will slowly plug up these tubes, and you will start building up some back pressure. And I've heard of a couple of Stanley guys that have said their pop valves are going off because of too much back pressure. That basically take those things off. Stanley literature will tell you to when you're putting the car away for the winter, drain all the water out of the water tank, fill it up with kerosene, fill the boiler up with kerosene, fill the condenser up with kerosene. Let it sit all winter and kind of dissolve, and then get rid of it. I guess it was a lot easier to get rid of that kind of stuff way back in the teens. But that's the way you cleaned it.
I tried that once on the non-condensing car with the water sight gauge, and then when I went to fill up in the spring, the gauge had to replace the gasket.
Mm.
So I guess a kerosene dissolved something.
Yeah. Stuff that's in there. The early first condensers actually had, if you look at the fronts, they're V fronts on the 1918 735 out here. Those radiators leaked. Those condensers leaked. Tom's got a book out here of factory notes. I was looking through just the Stanley car problems, and from what I can tell, the car I owned was sold in April, and in June it was back for a leaking condenser, and it was back again in September for a leaking condenser. Somewhere along the line it got the flat radiator put on it. So the 725 out here with its original V-shaped condenser on it's pretty unique. Pretty much takes care of everything that I had to present on the water system and the steam system. A couple things I put at the end of the notes as far as in the area of considerations. Tom has always taught us, and I think it's probably the most important thing to remember, is forget about the rest of the car. Know where the water is in the boiler, how much you've got, before you start trying to figure out a problem that you've got. If you don't have enough water, you ain't going anywhere anyhow. So if it's a fuel problem or something else, and you're trying to get the burner to run right, don't have it low on water and end up scorching the boiler or something like that. Scorching the boiler is obviously when there's not enough water, overheating the bottom, the flues all start to leak. The 3-tube indicators, which are on most of the cars out here, you kind of got to get used to what that thing is telling you for the car that you're driving. I think all of them work just slightly different. There are on some of the cars, and I added one on mine, my 5th blowdown is actually a small standpipe inside the boiler. Since those indicators have been known to mess up in anything like this, if I have any question about water on mine, if I open up the valve that's on the driver's left side of the car in the middle, and I get steam out of that thing, then I've got less than 4 inches of water in that boiler. I frankly don't trust this thing, which is supposed to shut the fuel off. I don't know how you test it. The water level indicator and all, you can kind of watch it work and this sort of thing. I don't know how you test this thing shutting the fuel down and tell how it's calibrated and how it works. It's hooked up, it's there, but I want, if that gauge isn't giving me the right number for the non-condensers, the water indicator, find out what's going on. In New Hampshire, we had a pretty good hill that we all went up. It all stopped. We're pumping, I jacked up the back wheel of the car. We're pumping water. A little while later, we see Tom motoring up the same hill, looking at us and smiling, going on his little way. If you're low on water, you need to jack up the car. The non-condensing cars, it doesn't matter which wheel you jack up because they're pumped, they're driven off the engine. On the condensing cars, they're driven off the right rear axle. So you can only jack up the right rear wheel to pump water with those. The stack blowers that are on some cars were never a Stanley accessory. They are, and you'll see, here's the tube that's down right in the top of mine. Basically, it's a steam line that goes into the exhaust pipe. And when you get a backfire or something in the burner, by turning on the blower, you can move a lot of air through the exhaust pipe real fast, which translates into a lot of air being sucked into the burner and up through, and if you've got a backfire or something like that, it'll usually suck it out. I guess the first time I had really driven a Stanley, the 735, we were going to Linvilla and stopped at a light and it took a couple cycles to get through. Well, the vaporizer got just cool enough that when the fuel steam automatic opened up by sending fuel, it backfired in the tubes. So I immediately shut it off, and I had made the curve, and there was a guy on a motorcycle sitting there and saw the fire out from under this car coming around the corner, to which I added to his dismay by opening up the steam blower real fast. So now I sucked all this fire out and would fly out under the car. His eyes were as big as saucers. There was a woman sitting behind him in a little Acura, and I swear she had her shorts depleted. So they do work. They have a real negative effect. They'll pull a lot of air through the system, so that puts a lot of cold air up against this hot boiler, especially for the non-condensing cars, copper tubes. That cold air can cause those things to start to leak because they'll cool off real fast on you. So if you crack that thing open, get it closed again, give it a blast of air to suck the fire out, but once it's out, probably it's not going to reignite. So then shut it back off. I've had the cars pop, and I will shut the blowers off and then crack them a little bit, even when I'm relighting the car, just to keep airflow moving through there. If the car hasn't been run for a while, I've got the pilot on, and even when I'm putting in the pilot fuel, I'll sometimes crack the pilot or the blower just a little bit to induce a real slight draft through there, just to ensure that the thing lights off and doesn't backfire on me. So I do use them, but you've got to watch the effect of the cold air on the bottoms of the boilers. Also, all that air, if you've been running and it's a traffic light thing like I just described, that grating all in there is good and hot, and you're not going to bring all this cold air into that grate and super cool that thing real fast. So you can crack these cast grates, so they can be helpful, but you can also wreck something with them pretty quick. One of the things to watch, especially if you're manually controlling the water of the cars, is something we call priming. Priming is where the water level gets high enough that the motion of the car and everything is sloshing around. You start to suck actual water up, start running water droplets through the throttle. Now it's getting down to the superheater, and the superheater is flashing that to steam. You'll a lot of times feel that as surging, uneven throttle response going on. You get too much of it, and the superheaters can't handle it, and it sends water back to the engine. It can pop heads, crack heads on the cylinders. It will probably, if the water gets into the piston rod side where the packing is, it'll shoot through there, cut the packing out real quick. The backstroke, there's nowhere for it to go, and that's where you can pop the heads off. Guy out in Colorado had a set of bent piston rods. Tom was saying he probably had water in that engine, and it got in there uneven and just cocked the cylinder or the piston rod or the piston a little bit and just bent the rods. There's a possibility of how that happened. So you've got to watch priming. Level road, you may be going along fine, and then once you start up on a hill or something like that, it may start. I know when I rebuilt the boiler on my car, the car was supposed to have an 18-inch boiler in it. And the one that was in there that was bad was 14-inch. Well, I built a 16. So I assumed that the water automatic had been lowered to compensate for the 14-inch change in boiler. So I raised it back up 2 inches. Well, it turns out it had never been changed, but I didn't know that. And when I initially started the car and tried to drive it, it didn't have any power, which is another symbol of what's going on. And I could put it on the dynamometer that my brother has at the shop where everything's nice and still, and the thing ran fine. But as soon as I took it out on the road, it just didn't seem to have the power. And I drove it over here to Tom's. It was really the first time I had the car out. I also have the dubious honor of being doing one of the things that a lot of Stanley folks do, and that is running it out of kerosene. and brought it over here. Tom didn't drive it. I don't know if you were here that day or not.
No, but I heard about it.
I don't think he drove it half a mile. I said, it's priming. So you just feel the way the throttle was running, hearing what it was doing. And it just happened to be, you know, hills and things like that. It run fine sitting on the level. But once I lowered the water automatic 2 inches again, put it back, measured his cars, put it back where it was, everything was fine. Symbols, the low water, you'll usually see steam drop off real rapid. The water Ouija tubes and all don't tell you anything when the car is sitting still. You've got to actually run the car a half a mile or so and get water pumping to get those tubes cooled off and get that thing to indicate right. So it takes a little bit of time to get that to go. So you could be sitting and that thing's not telling you where your low water level is. You can sit for a couple hours, lost it more than you thought, take off and the steam pressure starts to drop real rapidly. It's probably an indication that the water level is way too low in the car. Hopefully you've caught that before it's scorched, but usually you scorch it before you catch it. The only thing I've ever read about one of these boilers exploding has to do with low water, and that is where somebody had low water and put water back in it in a real hot boiler, and that water came in fast enough that it, while it was running the car, that it hit that hot steel and flashed the steam. Evidently the pop valve didn't work and the boiler cut loose. Now with all those flues in there, these don't fly apart, and with all the piano wire it doesn't fly apart, but it basically blew out either top or bottom and there was a big cloud of steam and this sort of thing. So right away they said it was a boiler explosion. But the thing to do is if you've got low water, make sure that thing is cool before you start pumping water back into it. It will flash. One other picture on this group is the one Billy was commenting on, is the blowdowns. We bring them back, open up the blowdowns and basically get everything out of the boiler, pump out all the water.
Yeah, whose backside is that?
So he's blowing down the 87. One of the things you get used to and learn is the difference between water coming out of those blowdowns and steam, and you, as it runs down, once it gets out of water, you'll both hear a sound change to those, and if you're watching the end of the pipe where the water's coming out, you'll see a change in that plume. If it's got water in it, it tends to fan pretty big, but as the water starts to leave, the water course is hitting the atmosphere and it's expanding. When the water's out of it, you don't have as much of that going on, and the plume actually gets smaller, and you can hear the pitch change, sound change between the steam and the water. Ones like the one on the side of here, I've come to find on my car, I'll open that up so it blows down, and I leave it open so the water level drops in the boiler and in this thing past that point. Once that gets to pure steam, then I don't see anything coming out. It's still open, but you just don't see anything. Maybe a real light blue mist. So pure steam is just almost clear. And, you know, we'll shut it down, let the boiler continue to drain on. You can, started to enjoy doing this, people see the steam coming off. Well, if you get out about 2 or 3 feet out, you can put your hand in that steam, it's cold. Because it's flashed. People see all that steam coming out, and you stick your hands in there. Nice hot water to get all the dirt and everything off. And Tom will put washing soda in the cars. So you got a little bit of soap, and get cleaned up while you're blowing down the car. So we'll blow all the cars down. Typically, in going from wherever the water level is to out of water is about a 200-pound change on your steam gauges. So if it goes down much more than that, you've probably run all the water out and shut it off. And if you're judicious about the whole thing, you can usually drive the car, at least from where Bill is, back in and park it with the steam that's left in the car. At that point, you need to close all of the valves. Both pump valves need to be closed, so that if you were driving, you would be pumping the water. Throttle needs to be closed. You also, at this point after that, turn the pressure retaining valves off if the cars have them. But essentially, everything is shut off. And the boiler will cool. The water tank will have filled the water tank. And as it cools, it will create a vacuum. And it will actually suck the water back up through the plumbing system and fill the boilers back up. And I've come in, like on the 76th the next day, checking to see, you check it on the water tank, you know where it was when you put the car away, and after you get to know the car, it should drop a certain amount, and you kind of learn where that is. You can tell whether it's siphoned full. But I've gone to the 76th, and you then open the throttles. You open the throttle and you hear this, just the last little bit of vacuum coming out of it. So it's pretty efficient doing that. Once the car has cooled off and you're sure it has siphoned, you want to open the throttles. This boiler is full of water, and you've got all the water valves shut, which means it's going to pump. So if you have to push the car to move it, it's going to pump water. And the boiler's full, the throttle's shut, it's going to build pressure real quick. And if you're not paying attention, you'll blow the pop valve off or break a line or something like that. So next day, throttles are open, so you'll see the cars sitting out here with throttles open. Also, the drips stay open. The throttles can leak a little bit of steam, and if that drip is closed, there's no place for it to go. The packings and everything else are tight. The car will decide it's going to take a trip on its own. So the only valve that's open when you shut the car, put the car away, is the drip. So it's a check, make sure the throttles are closed, all the pump valves are closed, and the drip is, in fact, still open. That is all that I had to present on the water and the steam system. Any questions? If there's anything.
I was a bit confused on the bypass valves when you say bypass is open and bypass is closed.